Hello, I'm joining you from Japan. I'm sorry I can't join you physically in Indonesia this time. I have to be here for a few very important meetings. So here we go. I've put that video online. It's going to be in a second on my side at least. It should be instantaneous for you on YouTube. So that below the YouTube video, if you have any question, you can just pop those questions in. At the time when this video will be aired, I might be in a meeting. That's what I'm thinking right now. So after the meeting is over at the end of the day, I will go and have a look at your questions and answer them. So don't worry about it. And today I'm going to talk to you about something that I have titled Multi-Scale Geospatial Analysis Combined with Geophysics and Numerical Modeling to Solve 21st Century Issues in East Asia. In the past, I've talked a bit at UMS as well, with the geography department notably, and one of the things I try to push are more technical aspects of science. So that's low-cost technical aspects that are adapted for Indonesia, or I think are adapted for Indonesia. One of my colleagues, Aditya Saputra at UMS, has worked a lot on those different methods. I'm sure that is going to help spreading them in the coming years. But today I would like to take a step back and talk about deeper, I think, issues that we have in East Asia. A lot of this science today is still dominated by what is being done in Europe, in North America, more and more by China as well. But those large countries, those large block of continental countries, are very different from, let's say, Taiwan, Indonesia, Japan, that are island nations. And those countries have actually a very different challenge ahead. So I'm going to try to concentrate on some of those challenges that I have identified and I work on. And hopefully it's going to inspire some of you working on those topics. And you're going to see there are a lot of differences between those different countries. But at the same time, let's say I'm going to talk about population aging. Population aging is going to come to Indonesia at some point. You have a few years ahead to think about it. And now it's actually the right time to think, well, what should we do? How can we develop better today so that we don't make the same mistakes that the Japanese people has done, for instance? So let me go first to my research framework. And the research framework is, as I was mentioning, within Japan, I'm looking at how the country itself is also changing. So you have on the top right here, those are the major cities. So you can see them all, a lot of them by the coast. And all of the cities by the coast actually are seeing more and more concentration of people. People concentrate there because the population is aging. You have less people in the countryside, and they tend to concentrate in the city. Those cities, however, are located very close to sea level. So with the sea level rise, we're going to have some issues there. And when the people actually get away from the countryside, all the work that was done in the countryside is not being carried out anymore. So how do you keep actually the maintenance of some of the structures in places where actually the forest is replacing all the agricultural land? So that's another issue which is coming and making things a bit more complex. So when you think about it, how do you maintain actually all your structures that you had before? Once you have the population aging, you can't anymore. And because the population is aging, then there is less money coming in. So when there is less money coming in, the tax coming in, how do you pay for all of that? So now that's one of the difficulties. And like Homer Simpson here, we might have been eating actually the best part of the donuts already. And we might need to look at how can we survive actually the different problems that we are going to face. And if you look at it on a diagram of a representative diagram that I took from Kumamoto City, what you can see is that the place where we live, which is here the floodplain, a bit like in Indonesia in some ways, is trapped between the sea level rise and tsunami on one side, and volcanic activity and mountain hazards on the other side as well. So it's a very narrow space. And within this very narrow space, we have a lot of different challenges that are going to arise from this. If you want an example, think about 2006 and the Bantul earthquake. People were running away from the Merapi eruption at that time. And while running away from Merapi, they also had the Bantu Gempa Bumi at that time that went and told them, well, you can't go this way either. So they were really trapped in between which way to go in that case. So you have all those factors coming in together. And as the PhD thesis of Aditya Saputra has demonstrated, when you're in the Bantu area, you have so many potential for earthquakes and fault movements that it's not a safe area either. So to do all of that research, usually I rely on a series of different methods that include data collection by bathymetry, using also UAV laser scanners to do GIS geomorphometry, and all that goes into either analogical model or physical model in a computer. And because I'm not content with only working with the surface, I also work with different elements on the subsurface. And today I'm going to present actually different research results that follow and have used those methods and that are important for the different points I made earlier. So in a few words, first, the slope hazards. Hazards from the slope at the intersection between geomorphology and forestry. So why do I talk about it? First issue. Again, because a lot of the science is dominated by Northern America, by Europe, by China, the soil that we have there are very different from the volcanic soil in Indonesia or in Japan. And actually it's necessary to reinvestigate some of the commonly known processes because the material itself is very different and tend to behave differently. So here I have one example of what can be done for that. For instance, this is a laha or debris flow, in that case, deposits. So you can look at the structure, the internal structure of the deposit using GPR and understand how to use different material stops, how much erosion occurs between layers. And this is something which is very important. A lot of the work which is being done is looking at the topography before and then the topography afterwards and calculate some form of volumes. But if you look at it in details, this cross-section here with the GPR, and that's we have on that side here, show that in the distal area, there is almost in that case no erosion below the deposit. But when you go actually upstream, you have actually places where you have signs of erosion. So while depositing debris flows are eroding. So if you want to actually make correct assumption of how much material is moving, you need to start not looking only at the topography, but what is happening underneath the topography, and that's very important. And you could use, again, as I was saying, like model or data that have been created in Europe or by the Westerners or in China, but island volcanoes and volcanic arc islands are very typical and different type of material, dominated a lot by rather, I would say, light volcanic material, can be volcanic ash, pumice, and those behave very differently. And there is a whole new array of research that needs to be done on that if we want to understand better how sediment move, but also the different disaster hazards and disaster risks. And on top of that, it has been all very often divided because those are very different topics. In places like Japan, where the countryside is being actually abandoned, or at least there is less and less people in there, we have seen a very rapid growth of the forestry and forest industry. It was there before. It's not the reason why it's there at this time, but it's also now expanding. And while it's expanding and there is less people to actually go and cut the trees and maintain the forests, we have more and more mass on the slope. And this biomass is actually also affecting slope stability and the risk downstream. So this is an example here in South Japan where we went to take some UAV data. You can see the landslide at the time. There is a debris flow that started on the other side. And very interestingly here, all the trees are gone. And all the trees are gone down in the river. And what is happening is going to actually affect downstream all the infrastructures. This is important because even if you retreat away from the source area of hazard, that hazard actually can still go and reach you somewhere else. So there is something that needs to be done, and there is something a bit different that needs to be considered, in the sense that we need to start thinking of coupling more all the root system, tree growth, water trapped during rainfall in the vegetation to assess stability of slopes as well. And this is one very simple example in the 2017 Kyushu AME event. So we don't have actually any good reliable data before the event. So we counted the trees in average area around the slope that failed and estimated that the average of tree density must have been the same here to calculate actually the number of trees that are gone. It's about 9,000 trees just for that small slope. So it's a lot of tree trunks reaching the water system and eventually going to impact, like you can see here, or you can see the slit dam here, and the infrastructure downstream. And then we started to estimate the volume and the mass of those. So based on the DBH measurement and trees that were not cut or broken in parts, we made a measurement of the size of the tree, sorry for that, and based on that started to look at the weight or the mass more exactly with a 10% error based on those different locations. And what we could find out of this is that for a river like this one here, we had about 238,400 square meters of forested area that went down, and that's about between 160,000 to 200,000 tons of drifted woods that reached the river. I'm not saying that all the material left. You have a lot which is trapped in here. But for one single trunk of a river, it's a lot of material coming in and impacting or destroying houses. And when you look at the Naragaya River, which is located just right in there, you can see that a lot of the slopes actually went down. And that's another interesting part. So you have in orange here, the traces where the debris flow went, and in green are all the landslide area. So why did it happen this way? So the main reason behind this is because we have climate change rainfall here. What is happening is that the sea level, or the sea temperature, was much higher than usual. And because of this very high sea temperature, we had unexpected high rainfall event in a place where relatively it doesn't rain that much on Kyushu Island. And because we had that stock of material on the slope, it all went very easily and created these issues. So that's another point I would like to make here. When you think about climate change, when you think about climate change rainfall, it's not about that yearly change in 10 or 15 or 12% that some people put forward. What is important is the fact that rainfall are falling now in places where it's used not to rain so much. It started to rain all of a sudden a lot instead of being spread more across a few months or a couple of weeks. So those variations are a variation of reason. And as a scientist, if there is something I would like to promote further, is the idea of a reason in science. There is a lot of an idea of like when it comes as a whole, how much comes, but there is very little research that looks at science as music in some ways, where reason will play a much more important role. And looking at the different starting zone of those landslides here, we can tie that back to the orientation of slopes, to the slope gradient. So what I'm trying to show is that slide here, is that actually a few very basic GIS analysis can provide very important insight on where the areas might be moving. So you have all those areas here that are all oriented in one direction, and that all show similar slopes as well. But if material starts to move, it doesn't mean that it all reaches the river. It doesn't mean that it all reaches actually the city. So where does it stop? So it stops actually in a lot of places where you have change in the slope gradient, and those change in the slope gradients are usually mixed or together in places where you have tributaries. I'm not saying that tributaries create the slope gradient change or that the slope gradient change is a place where the tributary occurs. I don't know which one of the egg or the chicken comes first here. What I can tell is from the GIS analysis, there are clear correlation between places where the tree or the drifted woods are stopped and places where things actually are converging or where we have slopes change. And that's quite normal. But again, this is a very simple thing that you can do with GIS analysis, geospatial science and geospatial analysis, and that can bring you actually a lot of insight of where is it dangerous, where is the trees going to stop, where is our actually sediments also going to stop eventually. And those sediments, again, as the trees, are very much linked to the slope parameters and the way the landslides come out. And this is another element which is important. It's not because a lot of trees leave the slope that they're going to travel easy. Actually, the landslide itself is very important. So what we could see in this area of Asakura from the research I have done is that actually deep-seated landslide, or at least not shallow landslide. When I say deep-seated landslide, it's maybe the wrong term. What I want to say is like 1, 2, 3, 4 meter thick landslide. It's still a shallow landslide, but it's not a debris flow, or it's not an unconsolidated material flowing on the slope. Those kind of landslides tend actually to move as a whole mass, keep the trees on top, like the one that you have here. And those trees actually are not being brought down further. You have a lot remaining on the slope. When you look at narrow landslide like here, this one, that looks more like a debris flow, it's all cleaned up. So what is happening? Why is it that this landslide here that has virtually less sediment moving than this mass movement here, why is it producing less tree debris? Well, the reason is because on those cases here, what we can see is maybe 10, 20, 30 centimeters of the first few layers of the soil are going to be totally dismantled, flow like an earth flow, low flow like a debris flow eventually. I'm not meaning anything around the sediment concentration here, just for you to imagine how it's moving. And this dismantled material is going to bring the trees very quickly down, almost floating on top. While on that side here, you have actually a sloping plane, which is underneath the soil, and that soil keeps some level of cohesion. And because it keeps some level of cohesion, the material which is on top, the biodebris, all the trees, are not going to flow out with the rest of the material. It's going to stay on the landslide. So you have some of the material that you can see here that has been pushed down, but at the same time, you also have a lot of the material that stays on the slope itself. So that's the main difference. So it's very important also when you do your spatial analysis that you think about it. Think about, well, how is the landslide moving? What does it mean? It's not only about the area, it's about the process itself. And if you want to push this further, the shape themselves, and that's why actually geospatial science is very important. The shape of that landslide play an important role. So I've drawn it here. So what we could see is that when you have a funnel shape, the exit is very narrow. It's very hard actually for that mass movement to get all the debris, including the wood debris, to exit in this location. And you can see it actually quite well on this. Now, if I go back to my idea of rhythm, what's coming first, how it's moving, this is important in that case as well. So when you look at this old system here, different landslide, all connected by a corridor of debris flow, we can see that actually what has been happening here is that this corridor here with that mass movement has been moving partially first, and then you have that mass movement that spread here, and further wood debris went and get trapped at the back. How can you say that? Well, if that debris there, this pile of debris and mass had been actually moved out by the movement that we have upstream, which is fed by those two babies here, well, all that would have been evacuated. It's not the case. It's still there. So you can actually look at what you have on your imagery and try to understand how your watershed is moving. what is moving first, what is moving second, what is being activated in the first place and then in the second place. And it's going to play an important role in deciding whether the material is moving or not. And so I did some very simple math on that and tried to understand what are the different factors that control those movements, whether the landslide have a short or long run landslide, whether the exits are broad or small, and how much trees actually remain on the mass movement. So on top of that, this is for like a natural slope. This is still in some form of volcanic material. When you go to volcanoes, you're going to see then different type of movement again. So we're going to move back a bit to Indonesia this first, and I'm going to show you some work in Indonesia and another place where I think there is a need of more work. And as Indonesian, you are in a very good place actually to follow up on that work and try to research a bit more on this. My thesis here is that there is no clear linkage between the deposits of a debris flow or of a process and the outcrop that you can see in the landscape. This is not a theory that a lot of geologists like or sedimentologist people like, because it goes against the very basic principle of geology and outcrop analysis. I am telling you then that what you can see in your outcrop doesn't relate to what is happening during a process. And here is the proof of it. So we are here at Semeru volcano in the Lengkong Valley, and we had cameras set up and camera filming actually the different processes, and those different processes like the Lahar here or Banjir leave deposits. And what we did is to go and compare those deposits with the video that we filmed. I will go back maybe later on the Merapi issue here. And what we can see is really interesting. So I did a few drawings to make it a bit clearer. Actually, for the same type of deposit, you can have different processes explaining them. And here the case I'm making is that for that series of layers that you have right here that you can see, those different layers, if you were to look at them in an outcrop, they would look like hyperconcentrated flow deposit. Very fine laminated work. And what we can learn from the video analysis and the outcrop analysis is that actually those very fine material can be deposited by a very coarse and high energy debris flow that doesn't look at all like the deposits it left. And here is a bit of an explanation. So imagine you have debris flow in your valley here, and it stays only in this. If you have balancing left and right, you can have actually on top here a very coarse debris and material which is being deposited on top. You can also have, let's say, in again that debris flow flowing, when you have an oversized clast moving. It's moving in the flow, but it's moving much slower than the rest, and it's creating a dam at the back. So the level is rising, and while the level is rising, you're having actually sediment being deposited. Depending on the size of that rise, you can have actually coarse material being deposited. But at the same time, if the level rising above that pseudo terrace, that level here, is very little, you're going to have only fine material draping the surface. And you can have drape like those ones that comes right in between. And once the debris flow is gone, you're going to have very fine drapes on the top that looks exactly like an hyperconcentrated flow deposit, but it's not. It's just one part of the debris flow that, because of the local conditions, created that deposit. And it's something that we don't see so often. We very often, or we always have almost a direct linkage between deposits and the process. So using geospatial science, image analysis, we need to actually observe better the processes and stop making assumptions at the second or minute scale. We need to start looking at those minor, what was considered as minor changes, because they can have major impact on what we are studying. And finally, I would like to talk to you about another volcano, but this time in Japan. It's something I'm doing right now. It's research at Unzen volcano. So Unzen volcano erupted in 1990s, between 1990 and 1995. You can see an aerial photograph of it here. And despite having this eruption stopped, a lot of the volcanic dome on top didn't collapse. They stayed right at the top, creating this series of different domes that you can see. So this is the figures that I took from the Ministry of Land and Infrastructure. So you can see the different dome writing on top of it. And this dome is actually moving about 10 centimeters a year. And something interesting there is that to protect the city down here, all around, they have created a whole series of sabo dam like you have on Merapi volcano. And those sabo dam are being cleared of sediments regularly using remote control engines. So this is not a small toy, it's a huge engine being controlled by remote sensing. And not remote sensing, remotely, sorry. And when you look at your volcano, let's see if the video is going to work. This is how the dome looks like. So the dome collapse creates a series of pyroclastic flow, and this pyroclastic flow then reach the main valley. And when you are in this valley a couple of years later, you have a series of lahar coming up. So what did we do here? So this is a few years back. Where did we go back? So the government in Japan wants to reopen that area to make it a geopark. So we are assessing the risk relating to the dome still sliding and potential lahar in this valley. So we use a set of different experiments, create this kind of 3D model to try to understand how the slope are changing, how they are evolving, and also understand where is the material coming from, where is it going to, and are we actually building up for future hazards, future disasters potentially if people get in there. And to complete the UAV and LiDAR data as well, we, as I mentioned earlier in this presentation, also use subsurface data like GPR here, like processing different data, starting from the raw data and getting information about the subsurface, so that we better understand how things move. So why did I get interested in that? It's because when I think about lahar, I think about what I've been studying, like generations of scientists going to the Philippines, to Indonesia, and seeing those events just after eruption. And one thing, going back to that idea of rhythm, is that the idea that we have about lahar and how they flow, how they form, is it just something which is related to an after-event idea? Or when you think about the rhythm of pyroclastic, of debris flow and lahar after an eruption, actually, are we missing some part of the story? Are we not seeing actually things that happen 5, 15, 20 years down the line? And Mount Unzen is a very good chance to do that. So concentrating on those hazards, but not right after the eruption, but 10 years down the line, can we learn new things? Can we actually look at how those lahar flow and do they flow differently? And the answer is yes, actually. So when you look at the LiDAR data combined with SFM data from UAV, you can see that it's really interesting. Lahar don't start from the top where most of the rainfall starts. They start from the mid-slope. And when you look at the mid-slope and the different change in the wall of the Lahar Valley, you can see that what is happening here. So in red here, you have the level of change. Those different levels here are going to actually drop in the valley. So you have the wall here, which is in red. It means that it's been eroded. It falls into the valley. It creates those lumps until those lumps of material accumulate enough. And you have a lot of pyroclastic flow material inside. It means that you have also fine material. So the water gets trapped behind during a rainfall event until it has sufficient energy to break that temporary dam. And that creates the momentum necessary to start short-lived lahar. So very interestingly, in those valleys at Unzen volcano, a lot of the lahars, at least all that we have observed in the last 3 years, do not start at the top of the volcano where you would expect it to start, with the steeper slopes, with material available remaining from the eruption. No, it starts actually by other processes. So you have intermediary processes coming in between, so on the valley wall, making them collapsing. And once they have collapsed, then you can have a lahar triggering. It's much closer to what you would see on a normal, a more traditional mountain, rather than what you can see on a volcano. And when you look at how the valley look like, so those are some photographs of what you can see. You can see also that there are a lot of very different dynamics. So when you look at the result from the GPR, what we can see is that we have layers like the one that you would see at Merapi volcano or Tsemelo volcano, but at the same time you also have trapped inside actually the side fan that are still remaining in the valley. And one of the reasons for that is because instead of being purely erosive, you have actually wills the different level or different wall collapse in the valley. You have base level that have been created. Those base level create a new local base level, so that instead of being erosive, you have your sediments that start to pile up at the back. And once they pile up, then it's a depositional feature. So instead of having pure, in your radargram, pure erosion or pure deposition created by very stratified and constructed event, you have actually a lot of different elements playing together and contributing to the valley formation, making actually the prediction of lahar in this valley much more difficult. And it's really important because 20 years down the line, people start to think, well, the eruption is gone for a while now, it must be safe, we should be able to go back and actually enjoy that space again. Well, this is one way of thinking about it. The other way of looking at this as well is the fact that because the processes are much more complex now, with all the processes, not just the lahar processes coming in, then you also have to be careful of what is happening in those valleys. And it's something that you might want to think about in Indonesia as well. It's not because the volcano is dormant that it's safe. So, in fine, what do I want actually to tell you? So I'm giving you in the end a last example. This time is on the floodplain. It's in Christchurch, and it's following the earthquake in 2011, where the land went down locally by 50 centimeters to a meter. So basically, the land was much closer to the sea level. So it was almost like a sea level rise. And in the years after that, we have seen the impact of sea level rise, the incapacity of rivers getting the water out at sea, the incapacity of the water system network to operate fully. And that's why you can see the photograph that you have on the image here, those different floods at different level. So I'm going back to what I said in the introduction. What I presented here today is very much linked to the issues that we have in the islands of the Pacific, especially the volcanic arc island, the large islands. And those are climate change related, rainfall change. How are we driving our population in this system? How do we use the land? Do we reforest places that are not in use? How do we control places that were forested before? How do we live with volcanoes and places that are active? And what kind of research needs to be done to actually better understand those systems? If we don't, and we keep the same level of knowledge, we know it's just not enough, and we can continue having actually issues. And it's something that needs to be said, because a lot of the work in natural hazard and disaster risk and all the management issues has been now concentrated on the human aspect. It's very important, it's essential, but this turn shouldn't hide the fact that the science itself on the processes is not quite there yet. We can't tell when a landslide is going to move next week or next month yet. Same for debris flow and same for volcanic eruption. So I hope that you see that the different issues that I've mentioned here are, for at least for the young scientists who might be in the room today, um, are issues that you need to look at. And because the economy is not going so well worldwide, both in Japan, US, China is not in actually a much better place. Indonesia still enjoys a bit of fresh air. I'm not saying it's going to last forever, but because of that, as scientists, we have to be responsible about how we use the funding. And when we don't do fundamental physics or those kind of research, I think it's important to do something for the community so that the research that we do benefit the community and that we actually help people living better and in safer places. So I hope that you enjoyed actually part of this discussion. And at the end, I would like to say another last thing. So I'm going to go to a last slide that I had. I have very good news, actually. My university and the University of Muhammadiyah Surakarta have signed a MOU so that we can exchange teachers. We can also work closer together. And students can also come to Kobe University, like my students can go also to UMS. Last year, I had 4 of my master and fourth year students going to UGM on summer program and going to Indonesia for different field research, and they loved it. So thank you for being so welcoming. Think about those of you who participated in those different summer programs, for instance, and I really look forward to working with you in the future. I'm really sorry I couldn't meet with our counterpart from Taiwan this time. I would have loved to meet with them. Might go to Taiwan myself in a couple of months for research on landslides, but if they also have interests in collaborating and developing research within East Asia, I would love to do so. Thank you, guys. And I hope to see you soon in UMS or in Kobe.